Hello, this is Che from Northeastern University. This is part 4 of the series on spectral clustering. So we have been going through one video at a time, and I have included a couple videos ahead of this video, specifically on the topic of Lagrange multipliers. Now, it's very important that you understand Lagrange multipliers before you move on to this video, or else you probably just won't understand anything. So, well, not anything. You'll probably understand something. But in any case, in today's problem, we're kind of doing an extension of Lagrange multipliers in matrix format. So now we want to find the minimum. We want to find the x vector that minimizes this whole expression. That's what this says. We want to find the argument x that minimizes this whole expression, subjected to the constraint of x transpose times x is equal to 1. We're also going to make the assumption that A and A transpose are the same, which means it is symmetrical. Also, we want to say that this is positive, semi-definite. Now, what does that mean, positive semi-definite? Well, you see, when we have numbers like 5, 4, 1, these are positive numbers. And we also have negative 3, negative 4, and those are negative numbers. In matrix format, there's also something very similar, analogous to this, called positive definite or negative definite. So a positive definite matrix like A, if it's positive definite, it means that if no matter what vector you take, x times A times itself is always greater than 0. So that's what it means when a matrix is positive or positive definite. Now, if a matrix is negative definite, you will have this times A times x always less than 0. So in those cases, that's negative. Now, semi-definite means that it's greater than 0 or it could equal to 0. So positive semi-definite, that's what that means. So you can think of like numbers as positive and negative. You can also see matrices as positive and negative. And when a matrix is positive, it means that when it's interacting with other vectors, specifically in this format, you always yield a number that is greater than 0. So anyways, in today's problem, our goal is to find the x that minimizes this using these constraints. It is a very, very typical Lagrange multiplier problem, except now we're applying this in a matrix format. So a very quick word on notation, which is like if we have min versus argmin, you will see people use the two of them interchangeably. Like very often people just use whatever they feel like using, and that's fine. I mean, it doesn't really matter that much, because they basically mean the same thing. The difference is when we are talking about argmin, we want the x that minimizes this whole thing. So the return, what we get out of this, is the x. When we're talking about min, on the other hand, we want to find the x that minimizes this, but instead of returning x, we return the minimized value. So that's what we get. The smallest possible value of that once we found the x. In both cases, we need to find the x. It's just depending on which value you return. But in general, you know, people use this interchangeably. I've seen both ways. So just keep in the back of your mind so you have an idea why sometimes people specifically use argmin versus min. So okay, now if we move on into a more toy problem in regular calculus. Let's say we have this right here. If we want to find the argmin, we want to find the x that minimize this, it's quite simple, especially if we can plot it out. It's very obvious that as the plot goes, the smallest possible value is at x equals to 0, right here. And to find this, you learn from calculus that what we want to do is take the first derivative. So it goes from that to this and set it to 0. Once we set it to 0, we solve for x. And from this, it obviously comes out to be 0. We also learn in calculus that, well, just because we found this point, it doesn't mean that it's always going to be minimum. It could have been maximum. Like here, for example, remember, we use positive 3x squared, but what if it's negative 3x squared? So it looks like this, and that looks like a hill with a maximum. If we take the derivative, similarly, we will get negative 6x equals to 0, and we will get the exact same point, x equals to 0. And therefore, it's important at this point that you want to find the second derivative. We take the derivative again and check that the second derivative is positive. If this is a positive value, it means that it's a minimum. Over here, if it's a negative value, it means that it's a maximum. See? So taking the first derivative tells us the point. Taking the second derivative tells us whether it's a maximum or a minimum. Now, this could be translated into the matrix format when we start dealing with argmax of this whole thing. Now, given that there is, subjected to this constraint, you have learned from Lagrange multiplier that when you face this kind of problem, what we do is we first move everything to one side of the equation and let that equal to 0. Then we put this together with the original formula, multiplied by some constant. Again, we take the derivative of this whole expression. And when we do that, the derivative of this, we learned previously, is equal to this. And this is making the assumption that A is symmetrical. And the derivative of this, you can see as x transpose times identity and lambda, right? So when you take the derivative, it's lambda 2 identity x. And the identity goes away, just 2 lambda x. That's how we got this from. And we set this expression to 0, just like this part over here. Set it to 0. And move this to the other side. Now we have this expression, which we can just cancel the 2. And that leads us to this final form. Now, this form, we still need to solve for x, but this form looks very, very familiar if you were paying attention to the eigenvalues and the eigenvector lectures, where if we have an eigenvector of A, if you have the eigenvector of A times A, you will get the same eigenvector back, multiplied by some kind of constant. And you will see that they are literally identical. They're identical formulas. So what this tells us is that if you want the x that minimizes this whole expression, x transpose ax, the x is the eigenvector. That's all you need. You pick the eigenvector, and that will give you the vector that minimizes this whole expression. Now, of course, similarly, we don't know if this will be a minimum or a maximum. So if we take the derivative of this, right, it becomes 2ax. Now, if we take the second derivative, it becomes 2a. So if this right here, this is a matrix, if this is positive, it will give us a min. If this is a negative, it will give us a max. So we just have to check whether this A is, right here. If this A is positive, if it's positive definite. And the way to check the positive definite in a symmetric matrix, right, is we take the A, find all its eigenvalues. If all the eigenvalues are positive, it means that A is a positive definite matrix. If all the eigenvalues are positive or 0, that will give you A is a positive semi-definite. Now remember, from the very top, I said that we're going to just assume that it is positive semi-definite. And therefore, since this is positive semi-definite, we know this is a minimum. And that's how we can tell. Now, the next question is, oh yeah, we have x, right? And we know x is the eigenvector, but there's a whole bunch of eigenvectors. Like, depending on how many eigenvalues you have, lambda 1, lambda 2, lambda 3, each one of them corresponds with their own eigenvector. So how do you know which one? Well, we know that eigenvectors are all the same size. They have a norm equal to 1. So v1, v2 is equal to 1. v3 is equal to 1. So let me ask you a question. Lambda 1, v1, lambda 2, v2, lambda 3, v3. Which one will be the smallest if they are all the same? Well, obviously, the eigenvector corresponding to the smallest eigenvalue. So this is the smallest, and this multiplied by this will give you the smallest possible value. So to recap, if we want to find, I guess I'll do it here. If we want to find x such that this whole expression is minimized, we look at the A itself and find the eigenvalues as well as the eigenvectors. If we can find the smallest eigenvalue, its corresponding eigenvector is the x that we're looking for. That's how we solve this problem of maximization, minimization. Of course, if you were to pick the largest, if you were to pick the largest eigenvalue, then that will maximize this instead of minimize this. And that's how this kind of problem works. So I guess this is good enough for now. Well, thank you for watching.